As we know, there are a lot of different geologic processes shaping the surface of the Earth, and not only the uppermost layers of the Earth, but also other internal layers of the Earth is being affected by tectonic processes. So at the surface, uh, one of the most important geologic processes responsible for shaping the surface of the Earth is deposition of sedimentary layers, erosion, and weathering. And on top of that, there are also tectonic processes. So this timeline shows how these different processes work together and shape the surface of the Earth and how they change the orientation or original position of structures in during tectonics and also deformational and non-deformational processes. So in T1, we have a non-tectonic or non-deformational depositional or sedimentological process, which is the position of formation B. A lot of particles, broken rock pieces, rock fragments, fossil fragments, minerals um, will basically come from air and they will settle down in a basin. And within that sedimentary basin, this sediments, rock particles, will form horizontal layers. So that's the depositional formation B. And all sedimentary units will form horizontal layers initially, and these horizontal layers will be parallel to the surface. This is stage one, and in the second stage, if sedimentation process continues in the basin, if more sediments are received by the basin, then sedimentary thickness of formation will increase over the time because on top of these two layers, there will be more layers forming on top of these two previously formed layers. If this region is tectonically active, in this case, there will be a faulting process or folding process affecting these previously formed sedimentary layers. In this stage, if it's faulting, let's say there is a lithuric fault, this spoon-shaped lithuric fault will result in rotation, block rotation in the hanging wall block because of the curvature or curved geometry of the fault plane. As a result of that rotational deformation, these previously horizontal layers will change original position and they will rotate. For this example, they will rotate counterclockwise and they will be tilted into the fault plane. On the other side, in the footwall block, layers they don't have to uh, be subjected to the same rotation process. It can be just a hanging wall deformation, or if it's a regional scale rotational deformation, all rocks will rotate together. In this example, we have a fixed footwall and more mobile deformed hanging wall. Because of that, most of the deformation is kind of confined in hanging wall block. After rotation, now these initial horizontal layers are tilted in one direction. If we add directions like west and east, now we have east dipping layers on the outcrop. After faulting, if this basin doesn't receive enough sediments, for some reason tectonic processes can stop or uplift around the basin can stop, and as a result of that, there can be a drop in sedimentation rates. That means this basin will receive less amount of sediment or even maybe none. So we call that non-depositional stage. Within this non-depositional stage, because this basin is now starving, not receiving enough sediments, that means there will be very limited minimum amount or no sediments coming and covering the surface of these tilted layers. Because the surface is not covered enough, it will not be preserved and it will be eroded away as a result of weathering processes and erosion processes. So this erosional stage, non-depositional stage, will form this erosional surface. So you can see these layers up here is now gone because of erosion. So we don't have these part of the rock unit anymore present within the basin. So it is gone. So this is an erosional surface. So this erosional surface will later form a depositional in unconformity plane. And in the later stage, in the last stage, let's say this basin receives sediments again, tectonic processes change sedimentation rate, and lots of sediments coming into this basin. So in this case, these new sediments will arrive, and they will cover this erosional surface and form this new set of layers. And these new set of layers will be horizontal again. So this bottom unit will be tilted because of the previous faulting event, and after erosion, newly coming sediments will form another set of horizontal layers on top of this tilted layers. Now you can see there is this angular relationship between horizontal layers and tilted layers at the bottom of unconformity plane. So this blue line, which is um, defining a big time gap between the position of two units, the position and the formation of two units. This is an angular unconformity. So in this case, this top unit is horizontal and bottom unit is tilted. It means during the deposition or at the time of deposition of formation A, formation B was already tilted. So if you plot these two units on StereoNet, since formation A is horizontal, it will be defined by this primitive circle where we have 0-degree dip angle. So this is formation A. And if you plot formation B, which is the bottom unit, and tilt it to the east, so these are, let's say, dip angle 30 degrees. So they will make a great circle curve to the east like that. We don't know strike orientation. Let's say this is north-south striking 30-degree east dip component. In this case, we will find a great circle with strike orientation to north-south direction and dip angle to the east, so which will make one of these great circles at 30-degree dip angle with define formation B. If we add one more step here and rotate everything together, let's say there is one more tectonic event in this region which produce one more rotational deformational state and rotate everything together. In this case, this is what will happen. This formation A at the top will be also tilted, and this formation which was already tilted will be tilted more. So in this case, the angular relationship will become, even this unconformity plane will be tilted. So in this case, this unconformity plane will be tilted like this, and top units, which used to be horizontal, will be tilted like this, and this bottom unit will be tilted more. So here you can see the angle of this unit is steeper than this. And these horizontal the units, so this is the surface of the earth. Let's put a 3 over here. So this is now present day configuration of formation A and formation B after a second rotation of the formation. And this is the unconformity plane separating formation A from formation B. So if you plot these two layers now, both formations will be east dipping because top unit formation A is relatively shallower dip angles, has relatively shallower dip angles. It will be a great circle closer to other circle where we have smaller dip angle values. A small great circle here, and this bottom unit is now steeply dipping unit, so which is almost subvertical. So that great circle will get closer to the center of the projection. Now we have two formations making a great circle because of the dip angle, even on conformity plane. So how can we reconstruct this deformation, restore this deformation stages, and go back in time and see what was the orientation of, what was the original position of this tilted layers at the time of the position of formation A. So we want to take formation A back to horizontal position and rotate everything together in the same amount and same direction. That way we can go back to this stage from here to from here to here. Okay. So we can do that with StereoNet. In this example here, I have two formations dipping northwest. So mark directions on our StereoNet first. So first layer has an orientation of north, let's draw that, north 15 east, 58 northwest, and second one is also north 15 east, 23 northwest. So you can see one of the layers formations is kind of gently dipping, but other one is moderately dipping formation. And this is the formation above unconformity A, and this is the formation below unconformity B. And which one? First, you have to decide which formation should be rotated back to horizontal. So you always want to rotate younger unit or top unit back to horizontal. And whatever amount of rotation you apply for to restore that deformation, you apply same amount of rotation in the same direction for the bottom unit. So let's plot these two formations on StareNet. I will show both formations with a great circle and pole, but all you need is pole. You don't need great circles, but just for this exercise, I will show both. So north 15 east can be marked here on the primitive circle. Count 15 degrees from north towards east. So 10, 14, 15. So I will mark this point as north 15 east. Then we rotate that tracing paper and move that point to north-south reference line. And we count 58 degrees from west because the direction is northwest. So we count 58 degrees from west. 10, 20, 30, 40, 50, 58 is right here. This is formation B, and I will find pole to formation B with this orientation. And to do that, we have two options. You can start from great circle and count 90 degrees in the opposite direction, or you can start from center and count dip angle of the unit in the opposite direction of dip. So it's dipping 58 degrees. I will start from center and count 58 in this direction. 1, 2, 3, 4, 5, 52, 4, 6, 8. So right here, we have pole P, B, for formation B. And second great circle will be north 15 east, 23 northwest. So in the same orientation, I will count 23 degrees from other circle. It is right here. And pole to this plane will be right here. And I will mark it PA. So this is the formation above unconformity. And which formation we want to rotate back to horizontal? A, formation A, the younger unit. So how can I move this plane back to horizontal? So basically, if you imagine this is the plane and this is the pole to the plane, if I have a tilted plane like this, its pole will be also plunging in one direction. If we have a vertical plane like this, its pole will be horizontal. So plane will be vertical and pole will be horizontal line. If we have a horizontal plane, in this case, this pole will be a vertical line. So where would you plot vertical line in projection? It is right here at the center of the projection. That means if we move PA, pole A, back to center of the projection and record the degree and direction of rotation, we apply same amount of rotation on the second point. We will be basically, everything will be rotated back to, everything will be rotated together in this case. So this formation will be rotated back to horizontal in this formation, and the second formation will be rotated back to exactly the same amount of rotation we applied on pole A. So how can we do that? We can move this PA to east-west equator, and in order to move this point to center of projection, we have to move this point from east to west, and it will be basically dip angle of the formation, so 23 degrees. So the measurement is 23 degrees northwest dip. That means this layer is presently dipping at 23 degrees to the northwest. So if we take that 23 degree back and make it 0, then we will be changing orientation of layer back to horizontal. So that's what we are doing here. So in this case, we move point B exactly same amount and same direction along the small circle. That's the key point. When you restore unconformities or apply rotation on StereoNet, you always move points along the small circles contain that point. You don't move this point orthogonal in any direction. Because point B is right here on this small circle, I will keep it in the same place and move it 23 degrees in this direction, which will be 3, 5, 7, 9, 11, 13. Right here. So this is that. So I'll show it with a triangle this time to make it look different than others. So this is pole B, I'll say prime, because that's the new pole after rotation of formation B. And now we need to find a great circle to that back to this pole, because that great circle will give us orientation of layer before the formation, before rotation. So in order to find great circle to pole B prime, we count 90 degrees. So first move that point to east-west reference line or equator and count 90 degrees in opposite direction. So from here, count 90 degrees. This is 8, 18, right here. So this great circle, I'll make it a different color. So this red one, red line, is the great circle with the dip angle of 1, 2, 3, 4, 44. So dip angle of this layer was 40. This formation was 44 degrees before, at the time of during the deposition of formation A. And you can see orientation, still same strike orientation, but dip angle changed over the time because of rotation. So it was 44 when at this stage, so dip angle of this formation was 44 when formation A was forming in horizontal layers. And then after second rotation, the layer became this one, which was 58 degree dip angle. So we basically restore this deformation with StereoNet. That means there was 11 degrees rotation of 11 degrees in this region.